So our fifth lesson in our series of lessons on integration is looking at an application of what we learnt in lesson 4 on definite integrals to find the area underneath curves. So last time we looked at the definite integral, which is an integral which has a specific value, which is evaluated using these limits of integration, a and b. When we've integrated our function to give us the integrated function I of x, we write that inside square brackets and put our limits on the right hand side, and we evaluate this expression with b and evaluate it with a, and the difference between those gives us the definite integral. And we noted that unlike the work we've done in lessons 1 to 3, there was no need for an arbitrary constant, a plus c, because this subtraction would mean the c is the same in both and it would disappear. So in terms of using this process to find areas, it's exactly the same as what we did last lesson. So we're going to integrate our curve, the function, to give us the integrated function I of x, and then we're going to evaluate that between these 2 points. So using the point x is b and the point x is a, and that gives us the area between the 2 points. So just thinking a little bit about where this comes from, if we have some area under a curve and we want to increase that area, and we can call that increase in area delta a, and that increase is generated by increasing x by a very small amount, delta x, and also the height of our rectangle, as it were, would increase by a very small amount, delta y. So this increase in the area lies somewhere between delta x times y, this smaller rectangle, and this slightly larger one, which has a height of y plus delta y and a width of delta x. So therefore, the area, that the change in area is somewhere between y and y plus delta y if delta x is very, very small. So as delta x tends or approaches to 0, so it's a very, very narrow strip, then the area approaches y. So integrating this function f of x will give us the area if we integrate with respect to x. Now, I'm not sure whether we really need to know this, but what's more important is can we apply it to some questions. So if we wanted to find the integral of the graph of, let me just switch that to dual display so we can look at that on there. So if we wanted to find the area between the curve y equals x squared and the x-axis between x is 1 and x is 4, we would integrate the function, which is x squared, between 1 and 4. So we know now that gives us x cubed over 3. So add 1 to the power, divide by the new power, and we're going to evaluate that between 4 and 1. So that would give us 4 cubed over 3, putting in the first limit, and then putting in the second one, 1 cubed over 3. So that gives us 64 over 3, take 1/3, so that gives us 63 over 3, which is obviously 21 units. Let's look at another example. Let's put on a page, another page to work from. Let's put that there. So we're going to have a look at integrating this function. So we don't always need to have a sketch because all we're doing is a definite integral. So integrating this function, let's add 1 to the power in the first term, divide by the new power, put 6 back. On the second term, integrating a constant gives us just x, and put that inside our square brackets. And let's put our limits of integration in there. So this obviously, we can simplify this a little bit further and call that 2 there. So when we integrate this now, we're doing the integral of, we've done the integral, we've got 2x cubed plus 3x, and we need to evaluate it between -2 and 2. So it might be worth putting some brackets in here because we've got a negative term. So let's do 2 times 2x cubed plus 3 times 2. Remembering what I said last time about substituting or showing that you're substituting the values in, and often gets you some credit. Take away 2 times -2 cubed plus 3 times -2. So all of that is 2 cubed is 8, so that's 16 plus 6 in that first bracket. Take away, so we've got -8 times 2, -16 plus -6. So again, it's worthwhile taking care. So we've got 16 plus 6, which is 22, and we're going to take away -22. So overall, that becomes plus, so we get an area of 44. Now, sometimes students like to write units squared. We're not given the units, but we can indeed just write units squared, although it isn't always necessary. So we're now in a position to have a look at exercise 13A, on page 299. And if you'd like to have a challenge, then there's a slightly different question. We're going to have a look at solving questions like this next time, or in a couple of lessons time, where we've got more complicated areas, and these are built up from doing maybe 1 or 2 calculations.